Evaluating Plant Community Response to Sea Level Rise in Everglades National Park by Kristi Wendelberger. How do you think sea level rise will impact Everglades National Park coastal plant communities?
Everything will be underwater at some point.
Do you think it's important to conserve rare plants or animals being impacted by climate change?
Certainly, why not? The part of your community, and you can't just leave. This world isn't just for the human being, right?
Because we want that extra reach.
Plant communities in Everglades are distributed across the landscape based on elevation, inundation, and salinity. Along the coast, tropical hardwood hammocks reside on higher elevation patches, supporting a freshwater lens and therefore less salt-tolerant species. Buttonwood forests, buttonwood prairies, halophyte prairies, and mangroves respectively move down the elevational gradient, increasingly supporting salt-tolerant species. Using remote sensing technologies, I'm comparing the distribution of today's coastal plant communities with those from 1981 to see how communities have changed over 31 years of sea level rise. Understanding how salinity stress affects seed germination and seedling establishment will help us understand which individuals will move out of the community first due to increased salinity levels. I gathered fruits and seeds of these 6 species from buttonwood forests and tropical hardwood hammocks to perform seed germination and seedling establishment experiments. With this information, park biologists will be able to detect plant community change and direction of change by noting which species they see reproducing in the field. Back at Florida International University, I sowed some of the seeds in petri dishes and sand, germinating them in a growth chamber, while in the greenhouse, I used the remaining seeds in seedling establishment experiments. Both of the experiment types used 0, 5, 15, 30, and 45 parts per thousand salinity levels for their treatments. Halophyte prairies, halophyte meaning salt-loving, have been seen encroaching on the buttonwood forest, pushing out the glycophyte or salt-sensitive understory that supports many of the rare plants threatened by sea level rise. To understand how halophytes may alter soil salinity in their favor, making the soil column saltier and therefore outcompeting glycophyte species, I performed a halophyte-glycophyte replacement design competition experiment. Mimicking natural dry season conditions, I used marl soil and watered the experiment from the bottom with 26 parts per thousand saline water. Soil samples are being taken over time at 9, 18, and 30 centimeters deep, allowing me to assess each plant type's ability to alter soil salinity throughout the soil column. I would like to thank the Melendez Wright Climate Change Fellowship for funding the majority of my research.